Gravity, the force that governs the motions of planets, stars, and galaxies, is fundamental to our understanding of the universe. It is responsible for keeping our feet firmly on the ground and for controlling the orbits of celestial bodies. Though gravity is an everyday phenomenon, it remains one of the most enigmatic forces in physics. The way gravity works has been the subject of inquiry for centuries, with monumental theories proposed by Isaac Newton and Albert Einstein, among others. Despite its importance, the true nature of gravity, particularly how it operates at the smallest quantum scales, remains a topic of intense debate. This essay seeks to provide a comprehensive understanding of how gravity works, from its historical context to its effects on cosmic scales, while also exploring the unresolved questions at the intersection of gravity and quantum mechanics. The historical understanding of gravity. 1. Newton's laws of motion and universal gravitation. Isaac Newton's work in the 17th century laid the foundation for classical mechanics, offering the first detailed explanation of how gravity works. Newton's universal law of gravitation states that every mass exerts an attractive force on every other mass in the universe. The force of gravity between two objects depends on their masses and the distance between them. This theory allowed scientists to predict the motion of planets and objects on Earth with remarkable precision. It also set the stage for centuries of scientific progress, establishing the concept of gravitational force as one of the fundamental interactions governing the universe. However, despite the accuracy of Newton's laws in predicting the motions of planets and falling objects, his theory did not explain the mechanism behind gravity. The idea of action at a distance, that objects could exert a force on one another without any direct contact, was unsettling to many scientists. Newton himself acknowledged the mysterious nature of gravity, famously stating that gravity must be caused by an agent acting constantly according to certain laws. 1. Einstein's general theory of relativity. The limitations of Newton's theory became evident in the early 20th century, leading Albert Einstein to propose his general theory of relativity in 1915. Einstein's theory revolutionized our understanding of gravity by describing it not as a force, but as a consequence of the curvature of space-time caused by mass and energy. In Einstein's view, massive objects such as planets and stars warp the fabric of space-time, and this curvature dictates the motion of other objects. Rather than pulling on other objects in the way Newton suggested, massive bodies like the Earth and Sun cause space-time itself to bend, creating what we perceive as gravity. Einstein's theory resolved several anomalies that Newton's theory could not explain, such as the way light bends around massive objects like the Sun. General relativity also predicted the existence of black holes, regions of space where space-time curves infinitely and gravity becomes so strong that not even light can escape. The validation of general relativity, through experiments such as the bending of light during a solar eclipse and the precise orbit of Mercury, has made it the dominant theory of gravity. The nature of gravity. 1. The concept of space-time. The key to understanding how gravity works, according to general relativity, lies in the concept of space-time. Space-time is a four-dimensional continuum that combines the three spatial dimensions, length, width, height, with time as a fourth dimension. Objects with mass cause space-time to curve around them, much like how a heavy ball placed on a rubber sheet causes the sheet to sag. This curvature is not a physical substance that can be observed, but a mathematical representation of how the presence of mass influences the structure of the universe. This concept of curved space-time has profound implications for our understanding of gravity. The Earth, for example, moves through space-time, but because space-time around the Earth is curved due to its mass, objects near the Earth, like satellites and astronauts, follow curved paths. This curvature is what we perceive as gravitational attraction. A similar principle governs the motion of planets and stars, as their masses cause space-time to curve, influencing the orbits of other celestial bodies. 1. Gravitational waves. Another critical prediction of Einstein's theory is the existence of gravitational waves, ripples in the fabric of space-time caused by accelerating masses, particularly those involving extremely large objects like merging black holes. Gravitational waves propagate at the speed of light and can stretch and compress the distances between objects. This phenomenon was first detected by the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration in 2015, confirming a century-old prediction. The detection of gravitational waves marks a new era in the study of gravity. These waves provide a unique opportunity to observe the most violent and energetic events in the universe, such as the collisions of black holes and neutron stars. Gravitational waves allow scientists to probe regions of spacetime that were previously inaccessible, offering insights into the properties of space, time, and gravity itself. Gravity on Earth, everyday experience. 1. Why things fall on Earth. Gravity manifests most commonly through the falling of objects. When we drop a ball or an apple, gravity causes it to fall toward the center of the Earth. The strength of gravity is proportional to the mass of the Earth, and inversely proportional to the square of the distance from the Earth's center. Near the Earth's surface, the gravitational pull is nearly constant, which is why objects of different masses fall at the same rate, ignoring air resistance. The concept of free fall describes the motion of an object under the influence of gravity alone, with no other forces acting upon it, such as air resistance. In a vacuum, all objects, regardless of their mass, fall at the same rate. This was famously demonstrated by Galileo's experiment at the Leaning Tower of Pisa, and later confirmed by astronauts on the Apollo missions, who experienced weightlessness as they were in free fall while orbiting the Earth. 1. The role of gravity in atmospheric dynamics. Gravity is not only responsible for objects falling to the ground, but also plays a crucial role in holding the Earth's atmosphere in place. The Earth's gravitational field pulls gases toward the planet's surface, preventing the atmosphere from escaping into space. This is why, without gravity, there would be no air pressure and no weather patterns. In addition, gravity influences the movement of fluids on Earth, such as water in the oceans, rivers, and lakes. The water cycle, evaporation, condensation, and precipitation, is governed by the gravitational attraction of the Earth. Tides, for example, are caused by the gravitational pull of the Moon and the Sun on the Earth's oceans, leading to the periodic rise and fall of sea levels. Gravity in space, large-scale phenomena. 1. Orbital mechanics. Gravity governs the motion of celestial bodies in space, dictating how planets orbit stars and moons orbit planets. The balance between the gravitational pull of a larger body and the inertia, or momentum, of a smaller body is what keeps satellites and planets in orbit. For example, the Earth orbits the Sun because the gravitational pull of the Sun keeps it from flying off into space, while the Earth's motion at a tangent to the Sun's gravity prevents it from falling into the Sun. Orbital mechanics, or the study of the motions of objects in space under the influence of gravity, is crucial for space exploration and satellite technology. Understanding gravity allows scientists to calculate the necessary speeds and trajectories for sending spacecraft to other planets, moons, and even distant stars. 1. Black holes and singularities. Black holes are one of the most extreme manifestations of gravity. A black hole forms when a massive star collapses under the force of its own gravity, leading to a singularity, a point in space where gravitational forces are so intense that they cause spacetime to curve infinitely. At this point, the laws of physics as we know them break down, and no information can escape, not even light. Black holes are surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. The study of black holes has led to insights into the nature of gravity, space-time, and the very fabric of the universe. For instance, recent research has shown that the properties of black holes may hold key clues to the quantum nature of gravity. Gravity and quantum mechanics, the unresolved puzzle. 1. The quantum nature of gravity. While general relativity has provided a robust description of gravity on large scales, it does not account for gravity on quantum scales. In quantum mechanics, forces like electromagnetism are mediated by particles, but gravity's mediating particle, the graviton, has yet to be discovered. This presents a significant challenge because gravity operates on scales much larger than the quantum world, where quantum mechanics dominates. One of the greatest unresolved questions in physics is how gravity behaves at quantum scales. Quantum mechanics has been successful in explaining the behavior of the smallest particles, such as electrons and photons. But when it comes to gravity, there are still many mysteries to unravel. 1. The search for a theory of quantum gravity. To bridge the gap between general relativity and quantum mechanics, scientists are searching for a theory of quantum gravity. Several potential candidates exist, including string theory and loop quantum gravity. String theory proposes that fundamental particles are not point-like objects, but rather tiny, vibrating strings. These strings could potentially explain both gravity and the other fundamental forces of nature in a unified framework. Loop quantum gravity, on the other hand, suggests that space-time itself is quantized, consisting of discrete loops, or quanta, that can be described by mathematical structures known as spin networks. Both of these theories aim to explain how gravity works at the smallest scales, but no conclusive evidence has been found to confirm either approach. The impact of gravity on our understanding of the universe. 1. Cosmology and the Big Bang Theory. Gravity plays a central role in cosmology, the study of the origin, structure, and evolution of the universe. The Big Bang Theory, which posits that the universe began from a singularity approximately 13.8 billion years ago, relies on our understanding of gravity to explain how matter and energy expanded and evolved into the galaxies, stars, and planets we observe today. Gravity's influence is also evident in the formation of large-scale structures, like galaxy clusters and superclusters, that are held together by gravitational attraction. 1. Dark matter and dark energy. Though gravity provides a clear explanation for the motion of visible matter, it cannot fully account for all observed phenomena in the universe. For example, the rotation of galaxies and the movement of galaxy clusters suggests that there is more mass present than we can observe. This has led to the hypothesis of dark matter, a mysterious form of matter that does not interact with light but exerts gravitational influence. Similarly, the accelerating expansion of the universe suggests the presence of dark energy, a form of energy that works against gravity to drive the universe's expansion. Both dark matter and dark energy remain some of the most pressing mysteries in cosmology. The role of gravity in the formation of stars and planets. 1. Gravitational collapse and stellar formation. One of the most profound phenomena where gravity plays a critical role is the formation of stars. Gravity is responsible for pulling together gas and dust in molecular clouds, initiating a process known as gravitational collapse. When the gas particles in a cloud become dense enough, the force of gravity causes them to collapse inward, heating up as they do. This process leads to the formation of a protostar, which continues to grow as it draws more material in from its surroundings. Over time, the temperature and pressure at the core of the collapsing gas become high enough to initiate nuclear fusion, marking the birth of a star. Gravity not only triggers the formation of individual stars, but also governs the formation of planetary systems. As a star forms, the leftover gas and dust surrounding it begin to coalesce due to gravitational attraction, eventually forming planets, moons, asteroids, and comets. The gravitational interactions between these objects continue to shape the structure and dynamics of a solar system throughout its life. In this way, gravity is responsible for the creation of the very building blocks of life and the complex systems we observe in the cosmos. 1. Gravitational influence on planetary interiors. Once a planet has formed, gravity continues to play a vital role in shaping its interior structure. The force of gravity causes materials within a planet to compress, leading to the formation of distinct layers, such as the crust, mantle, and core. The higher the mass of a planet, the stronger the gravitational pull, which can result in a more intense differentiation of materials within the planet. For example, Earth's gravity causes heavier elements like iron and nickel to sink to the center, while lighter elements such as silicon and oxygen rise toward the surface, forming the crust. Gravity also influences the planet's geophysical processes, such as plate tectonics and volcanic activity. The motion of tectonic plates on Earth is driven by the heat produced by the planet's internal gravitational compression, combined with the heat generated by radioactive decay. In this sense, gravity not only influences a planet's formation, but also its ongoing geologic activity, playing a key role in the dynamic processes that sustain the environment. Gravity and time. The relationship between gravity and time dilation. 1. Gravitational time dilation. One of the more fascinating and mind-bending implications of Einstein's general theory of relativity is the concept of gravitational time dilation. According to this principle, time passes more slowly in stronger gravitational fields. This means that the closer an object is to a massive body, the slower time appears to pass from the perspective of an observer further away. The effect, although imperceptible on Earth, becomes much more significant near extremely massive objects, such as black holes or neutron stars. This phenomenon has been experimentally verified using precise atomic clocks. For example, clocks placed on satellites orbiting Earth run slightly faster than those on the ground due to the weaker gravitational field in orbit. On a much larger scale, the difference in the passage of time near a black hole can be immense, with time essentially coming to a standstill at the event horizon. This has profound implications for our understanding of the universe, suggesting that time itself is not a universal constant, but rather is affected by the curvature of space-time induced by gravity. 1. Implications for space travel. Gravitational time dilation also has significant implications for space travel. If astronauts were to travel near a massive object such as a black hole or a neutron star, they would experience time at a much slower rate compared to people on Earth. This effect could potentially allow for time travel in the sense that astronauts could age slower than people who remain on Earth. While this may sound like science fiction, it's a real consequence of the way gravity warps space-time. However, due to the extreme conditions required to observe significant time dilation effects, it remains a theoretical consideration rather than a practical one for current space exploration. Moreover, the understanding of gravitational time dilation could help improve the synchronization of clocks in satellite networks, such as GPS. Since these satellites orbit Earth in a weaker gravitational field, they experience time at a slightly faster rate compared to clocks on the ground. Engineers must account for this difference when calibrating the satellite system to ensure precise positioning data. In this way, gravity's effect on time plays a crucial role in modern technology. Gravity is a fundamental force that shapes the universe, from the motion of planets to the dynamics of galaxies and the very structure of space-time. Our understanding of gravity has evolved from Newton's classical theory to Einstein's revolutionary concept of curved space-time, with modern developments continuing to expand our knowledge. However, questions remain, particularly in reconciling gravity with the principles of quantum mechanics. The ongoing search for a theory of quantum gravity promises to reveal even deeper insights into the nature of the universe, offering the potential for new discoveries that could change the way we view reality itself.